Hello. Nice meeting everyone. My name is Yaron. I'm co-founder of iguazio. It's a company in the real-time analytics space. I won't touch too much on our product, but more on an approach that I'm presenting. Some of my previous background, been vice president in some companies, technology, worked a lot with the cloud service providers, built some databases. What I'm going to focus today is delivering AI in real time, because a lot of people are working with AI, Jupyter Notebook, CSV, Spark, etc. But that's not really translating into what I call actionable analytics. So what we're going to spend the time is talking about how to turn AI to something which is more useful and works with the business. So if we think about big data and analytics in general, and we started more with approaches around data warehousing. So we stored a lot of data in a data lake, and we used to ask questions, and those questions sometimes took hours, sometimes days. It wasn't that critical because we did page ranking. That was the first purpose of Hadoop. And then we started wanting to ask more interactive questions. We wanted to see graphs and charts, so we brought Tableau in, and we brought some other analytics and visualization tools, but it's still pretty interactive. And the thing about interactive is that we bring someone is asking a question, and then he sees a result, and then he needs to interpret it and do something with it. Most of us don't do much with what we see. Okay? So the world is moving now to what we call event-driven analytics, which means that machines interpret information, and those machines, based on that information, they need to react. For example, if you're taking Alexa, that's the most basic example of an event-driven analytics. Someone is talking to a machine, that thing is being classified, and you're getting a response. Another thing is like web recommendation engine. I'm going into a web page, I'm taking this data in order to, someone is analyzing my features, my preferences, and based on that, I'm responding to a user. Same thing about IoT. I'm doing predictive maintenance, so I get information from a bunch of sensors, I'm cross-correlating that with historical data, and I need to respond. So that is what I call event-driven analytics or real-time analytics, is things that get information in, needs to classify, and then need to respond. So the overall approach that we see more and more now is moving from being reactive, which means storing data in a lake, trying to analyze it, and coming with some questions, into things that essentially are applied to a business problem, are stimulated into a business application, whether it's a trading platform, or a predictive maintenance platform, or a user interface that's becoming more and more intelligent, or voice-driven interfaces, and that's what we're seeing today in the market. Okay? And I'm going to talk about some approaches which are slightly different than what we're used to in this space on how to tackle this problem. The other thing which is pretty related is the notion of cloud and edge. A couple of years ago, everyone told us, go into the cloud. That's the best thing since sliced bread. But since then, we've seen that as we're starting to analyze more and more data, a lot of the data has some gravity. So everyone is talking today about deep learning, analyzing video feeds. Some supermarkets and applications that we work with have 1,000 cameras in a supermarket observing shelves. I cannot send 1,000 camera feeds into the cloud and go and analyze it in Google Cloud. So what we see more and more is the need for different verticals, whether it's retail or automotive, connected cars, manufacturing, gaming, etc. The notion of having some analytics happening close proximity to the actual data generation. Another thing which is very interesting, if you look at the way the internet is designed, everyone thinks about the network or the internet as sort of a flat mesh, fully connected. It's not really that way. It's a lot of bumpy roads that connect the internet. That means that when things like 5G are going to go into production, we'll have huge amount of bandwidth within the metro landscape, within the cities, between one area and the other area within the city, but between cities we won't have a lot of bandwidth. So another phenomenon that you're going to see more and more is essentially the distribution of the cloud, the distribution of the internet. That's why you'll see Satya Nadella from Microsoft and guys from Google and Amazon starting to speak about the edge quite a bit. So, and those two things sort of connect, because what we see is that where you'll do learning is probably where you need a large resource pool of elastic resources and GPUs and lots of data and archiving. But where you'll do the inferencing, the thing that acts, is probably close proximity to the data itself. So that's just a prefix before we're diving into the actual presentation. Now, out of curiosity, how many of you are like data engineers, and how many would you categorize as data scientists? So how many data engineers? Raise your hand. And who's a data scientist? Okay, there's a majority of data engineers here. Okay, so one of the things that when we're trying to apply analytics and AI, we have good solutions today for data scientists when they're trying to have their own playground. You know, I know most of the people here probably use Spark. I assume everyone is using Spark. But still, most of the people out there, when they tackle AI or they go to university, they probably play with some pandas and CSVs. Okay? But even when they're going to Hadoop, they can do very interesting things in batch. Essentially, they take lots of data sets from different sources, they convert them to Parquet or CSV, they start analyzing them. Now they have a bunch of variants, it's got many different questions, it's predictive, it's intelligent, but if you're trying to operationalize that, there are a bunch of challenges doing so for real applications. So first, most of those things, once you've gotten the question and the answer, you'll see that it's not actionable. Okay, I got a response from my Jupyter notebook. What am I going to do with that response, and how is it going to impact my application? The other thing is, I'm collecting on my Jupyter or my Spark or Zeppelin, I'm collecting all those different data points. It took me 2 weeks to get approvals to get from different organizations. But if I'm building a real-time application that essentially need to classify information based on 1,000 features or 100 features that come from operational databases, real-time feeds, historical data, how can I really gather all that information to form a feature vector and classify it in real time? So that's almost impossible problem because of both political and technical challenges. Political because no one wants to get me access to some of the data, and technical because it's really hard to get all those different data points in real time to assemble this feature vector that in sort of the data science class was really, really easy to do. And there are obviously a lot of other challenges. How do I run exception handling and security and change versions on the fly and update my model and so on and so on. And eventually, sometimes I need to run the same algorithm in many locations, and I have mass problem of distributing my artifacts, and my artifacts are usually a combination of code and models and different things. So we need to start thinking how to tackle this problem. There is some answer that everyone taught us in the school that's probably the playbook answer. It just doesn't work so well. So what everyone taught us is this Lambda architecture, that we have a real-time layer and a batch layer. Okay, the batch layer will do slow stuff, but on lots of data. A real-time layer is really expensive because it's all in memory. So we'll just put a small amount of data. And whatever we're observing on our streaming pipeline, we're going to use it in order to make decisions. But good decisions are usually based on as many variants as you can possibly find. So if you think about a decision on, let's say, predicting stock, okay? If I'm predicting stock just by looking at open, close, volume information of my trading, and I don't cross-correlate it with information about the trader, with information from Twitter about the company, with information about the overall status of oil prices in the world, probably my decision won't be as accurate as if I would incorporate all those things. So stream processing is very nice for observing things on the pipe, starting to do windowing, but it's not really good for real-world problems that you want to work on many variants. So there's a different approach that I'm personally pushing and promoting and blogging on, which is sort of continuous analytics. It's a slightly different approach, a little more modern, based on microservices. But the general idea is that if we're looking at the real-time pipeline, there are a few steps in the process. So the first step is decoding and indexing the information. What does it mean? My information is structured or unstructured. It could be pictures that I have to classify and extract some tags out of them. It could be text that I need to take the text and translate it into sentiments. It could be some JSON structure that I need to classify and extract just the meaningful data. And I want to index it because then when I'm going to join this feature vector, I need some indexing into play. I cannot just work on Parquet files, which are unindexed, and work everything as one straight column. I have to be able to fetch just what I need. The next level in this pipeline is building the feature vector. So building the feature vector means that essentially joining different data points from different data sources, whether they're operational data sources, environmental, like weather, traffic condition, etc. Operational data sources, like what's the balance amount of this customer right now, it probably makes an impact on his buying decisions. So the second phase is enrichment. And then once we've assembled the feature vector, we're going to feed that into an algorithm. It could be in Spark or PyTorch or TensorFlow, whatever framework we want. We're running this feature vector into that decision mechanism or prediction mechanism, and we get a result. Once we've gotten a result, we still need to do something with that result. It's not just like in data science class, we get a nice result, 90% accuracy, we're all happy. Good. What are we going to do with that result? Whether we want to send a Slack bot, whether we want to close a system or shut down a firewall or whatever, it all requires this action. Maybe just we want to have a nice real-time dashboard, but still we need to translate those results into something that's meaningful for the business. And one of the ways to connect all those dots, first, all those things could be microservices instead of just jobs. We're used to think about jobs. We're submitting a Spark job, and it takes a few seconds just for the job to load. We need to think more like microservices, that each one of those things is a microservice, and the thing that glues those together is a persistency layer. So if I've taken some data, ingested, throw it into some database, which is persistent, and then the other guy in the chain that does enrichment can essentially just run a query. If I do everything in Parquet, I cannot just say, give me the balance for this customer. I would need to run over a gigabyte file to find this individual customer where I just got the message. So we need a mechanism of persistent, random indexed layer that allows me to do all this data stitching. And really the measurement that we're looking at that solution is we're trying to lower the time to action from the minute we get this sort of feed or event feed until we get sort of the decision. And the second factor we need to look into is throughput. So how many decisions can I make per second? And we cannot always micro-batch because micro-batching has its impact in latency. So that's the general idea. I'll give you some examples. So this is an example I worked on with the automotive company on fleet management. So the first thing that we get is we get a message from, let's say, a car, sends us ODB data, which is all those sensors, fuel, direction, GPS location. And this thing, the first thing that we may want to do is we want to contextualize this information because the car is sending us geolocation. Is the car on the road? Is the road jammed? What's the weather? Is it sunny or rainy or snow on that specific road? So we need to combine this data with, for example, geodata, previous state of the car. Is it now turned on or turned off? So I know it is starting to move, etc. So the first thing that we need to do is essentially assemble this feature vector. The second thing is we may not need to be too smart or too artificially intelligent to make some simple decisions like, oh, the car has moved. I can identify an event and I can send it to a message queue for something else to deal with that event. Or maybe I've identified a traffic violation by this driver because it just changed the speed and the road limit is 60 miles per hour and just driving 80, okay? And by the way, I already reported that, so I don't need to report it twice. So I need to also preserve state as part of that application. And maybe even do other things like geoaggregates and start drawing the cars moving on a road, and which is essentially a table of geolocation. But then I may want to drive intelligence into the decision. So once I've built a feature vector with this parallel enrichment process, which is more asynchronous by nature, I can take all this enriched feature vector with all this information that I gather, including historical data, actual data about the car. I can send it to a message queue like a Kafka, and then have Spark work on that and generate prediction. Like, for example, when is the fuel going to finish? When is that car going into a direction that's not supposed to do, etc. But those things can be in a delay of, let's say, 5 seconds. There's no critical need to have that in the real time. So someone may want to observe the dashboard, which will present real-time information about the location of the car. But in a parallel process, I can run Spark to start adding and labeling the data with more insights. And Spark can essentially also add information on the car table that either could be fed back into the enrichment or real-time decision mechanism, or be viewed by dashboards and other tools. So that's an example of how do you apply this technique on a real problem. So this is how we usually think about the problem. How many people are deploying Spark on Hadoop here? Okay, not more than 50%. How many are using Kubernetes, for example? Okay, fewer, but starting strong. Anyway, that's how they taught us to do big data. Okay, so take a file system, which wasn't really the greatest file system. It just worked for scale, oriented to what it was supposed to do initially, which is reading lots of big files. It wasn't about updating. It was just for batch ranking. And then we did some database, not the best, that works on that file system, and created a very specific orchestration layer called Yaron. And then we had some things that most of them are rest in peace by now. And there's only one thing that's sort of left out of that entire stack, which is sort of Spark, which is really a good thing. You know, the Yaron is not really the best scheduler in town, and HDFS is probably not the cheapest and the best file system in town. So what we were seeing is that, you know, after we spent all that DevOps, that the stack is changing. The stack is changing to become more, I call it cloudy or cloud native-y, which is essentially when we go to Amazon or we go to a cloud provider, we don't go and install necessarily HDFS. We'll just go and use S3. And if we need something more structured, we'll go and use BigQuery or Redshift or DynamoDB or any other database as a service. So that is becoming our persistency layer, whether it's structured or unstructured or streaming storage. And then the next layer that we're going to see is Kubernetes. What's great about Kubernetes is that all the cloud providers and also on-prem have exactly the same API. So now I can start and deploy my application on a cluster that can host any workload, not just Spark and Kafka, but also my Jupyter Hub, my TensorFlow, and anything I could think of, and serverless functions, which we'll get into. So essentially now we have one layer of persistency, which I could categorize as unstructured, cheap storage like object storage, and then something which is more structured like database as a service of the different kinds. The next layer of orchestration will be something like Kubernetes, and on top of it we'll have different middlewares, things like Spark or TensorFlow for analytics, things for user interaction like Jupyter Hub, and things that are more ad hoc computation for serverless, and on top of that, you're building your application. Now, another thing to observe, when you're going to the cloud, you're essentially not going to build Kubernetes by hand. You're just going to go, probably, depends, everyone has his preferences, you're probably going to take GKE on Google. You're not going to go and deploy your own operating system. And if you're using database as a service, you'll just consume whatever out there. It's not a good practice to go and invent your own database and starting to deal with all the security aspects and logging, persistency. So what we are seeing is this trend of consuming the lower layer and developing or innovating in the higher layers. So that's sort of, when we look at the stack, that's the way I see the future way of dealing with data applications. So, and the other thing that is, we're seeing it more and more is the introduction of serverless frameworks into the mix. Those are sort of the workhorse that allow us to do stitching, because now when everything is becoming services, database as a service, analytics as a service, AI as a service, all I need is some things that glue things together. Take an API request, go and call a service on the back end, do ETLs, do transformations, do inferencing, etc. So, and that's going to reduce all of our ongoing work on development, because mostly we just write code 20% of the times, but then we operationalize it about 80% of the time. And we need to do it over and over every time we go and fix a bug and change something in our code. So what we're seeing in the area of serverless is that you write code, you provide some spec, and then you push it and you let the serverless framework go and do the work for you. One of the things that we've done in iguazio is essentially come with an open source serverless framework called Nuclio. Pretty fast ramping at like 2,000 something stars on GitHub. You can ask Kelsey Hightower what he thinks about it, but is a good fan of it. But anyway, so it's a crazy idea, like serverless is something that the cloud provider should provide you, but we thought that there are several issues with Lambda, and we had to address them for our sake, and also contributed to the community. So the first thing is Lambda is so slow, it's extremely slow. So it takes you hundreds of milliseconds to process something. Nuclio is about 0.1 millisecond latency. It can do about 400,000 events per second on a single process. Lambda does about 1,000 on a good day. Okay, so there's a huge difference in terms of performance, and where you're analyzing data, you need concurrency. And when you're doing random transactions and inferencing, you need lower latency and faster processing. The second thing is that instead of having a stream processing engine that knows how to deal with checkpointing and redistribution and all that, and serverless frameworks that do other things, mostly focus on HTTP, we decided to embed the streaming capabilities into the serverless framework, and also opened it to all the different messaging and streaming protocols you can even think of. It's now part of a standard that we've initiated called Cloud Events that's maintained by CNCF. And the last thing, which is also not so trivial for serverless, is add state. So mount a file system into my function, or allow a persistent database connection into my function, or persistent cache. So we can start do very interesting things. And by betting on an open source serverless framework like Nuclio, you can now write your code once and deploy it in many places, whether it's the edge, on-prem, any cloud, any Kubernetes cluster. So that's another advantage. And now I'm going to show you how it could be used in a real application. This is an application that we work together with one of the large cloud providers and one of the biggest automotives in Europe. This is a manufacturing application for real-time predictive maintenance. So the general idea is that I'm going to, in this case it's Azure, I'm using Spark on Azure to build all my machine learning models. Once I have my machine learning models, eventually I have a file. I can take this file and push it into the edge. In the edge, we have sort of an appliance, a couple of servers, high availability. The first thing that you do is essentially get the messages from the machines. The machine generates sensor data, pressure, voltage, vibration, etc., errors. Some things are obvious. You know, if a machine is saying there is an error, I can just trigger an error. But other things that if I need to do prediction, the interesting thing, I cannot do prediction on my raw data, because any algorithm will essentially go and use prediction on standard deviation, variance, statistic window aggregate. So the first thing I need is sort of a time series database that knows how to take huge amount of feeds and start aggregating them so I can generate the things I'll use in the model. The second thing, I need to start doing prediction. So the prediction requires me to create a feature vector. And the feature vector comprises of different things. So the first thing in the feature vector is obviously those statistical aggregates from all the sensors. But the second thing would be environmental, pressure, humidity, temperature in the overall location, historical information about the machine itself, and other attributes. And I obviously need the machine learning model. And one of the interesting things that I'll show you is that essentially I can run Spark within a serverless function. And then we also need to move some data, because after a while we've gathered some more statistics. We can compress them and do a trigger every few hours, just compress the data, upload it into a blob store in the cloud. And we can also listen on a trigger with webhook. Every time there is a change in the cloud for some data, we can go and pull the image from the cloud and reload everything up. So this is an example of an edge application which is developed in a combination of cloud services running Spark in the cloud, and then inferencing that actually runs in a serverless engine like Nuclio, and just being triggered by HTTP or any event. Not so typical for Spark. You would probably see Kafka or those things are typical solutions, but sometimes you need event-driven decisions. And Spark is not really designed for event-driven decisions, for an HTTP request or things of that nature. So I'll show you what I mean by that. Second. Okay, sorry. Logistics. Oh, good. Okay, so again, what I can do, the first step, I can go, I'm using our cloud service to demo. So essentially, I can first go to, for example, this is Jupyter Hub, and I can go and build my model. And my model, that's a standard model with random forest. I can do data preparation and training, and eventually I generate a file which provides me the machine learning model. I can also run the prediction itself within the same Jupyter, and just to verify my function. And then another thing that I can do is essentially once I've finished writing an application in Jupyter, one thing that we're working on that is automatically going to generate the Python code that I can use in a serverless function. It's still not fully baked. We're still working out some things, but the general idea is that once I finish my training and my exercise on Jupyter, I can just click one button and it generates my Python file for the inferencing code. And thus once I've done that, I can just go into Nuclio. By the way, that's how also the open source version looks. That's the commercial distribution, but it looks exactly the same. There's no difference. And I can just go and see my Spark code that essentially does inferencing. It just gets an event, then does a classification, etc. And I could also load up my model into the function, all that in the same place. Now, one of the challenges with something like Spark, it has a huge amount of dependencies and things that I need to set. And that's something which is really possible in Nuclio. I can just decide what's my Docker image that I'm basing on, and I could go and define all my dependencies for PyArrow and Spark and Java and all those things. I could just go and define them as part of my function specification. And then when I do triggering, I could decide what triggers the function. It could be anything from HTTP event, cron event, Kafka. You know, if I'm going to choose Kafka, I'm just going to need to specify the address of my Kafka. You know, if I decided to go and use Kinesis, I'll just need to put my AWS key, etc. If I need Azure Event Hub, by the way, it doesn't change anything in my code. In Lambda, when you switch trigger, you have to start changing your code. So here I can now essentially take my inferencing code and run it within a function, and it will auto-scale. So if I'll need more inferencing requests, it will essentially just go and auto-scale. Now, it's not really limited to Spark. I could do the same trick exactly with TensorFlow. This is TensorFlow function example, which does based on the inception model. That counts, by the way, part of the template library. And I could do something very easy. I'll take in the testing environment, I can just take a URL to a lion. Let's see if it's being classified correctly. Yes, we have a lion. And also, TensorFlow has the same challenges because TensorFlow also requires probably a bigger distribution with Jessie or Ubuntu, and has all those dependencies on Conda and all that stuff. And Another interesting thing, I don't know if you can see that, one thing that I'm doing in this build for the TensorFlow function, I'm doing wget to load the model into my function. So that means that my Docker image, which is my new function, contains the model and the code. So all those people that are starting to sell you solutions to how do I make sure that my code runs with my model, there's a very simple thing. Just Dockerize both of them in the same artifact, give it a version, and that means that when I'm using my TensorFlow code, it's going to use the same model. And when I'm going to do any change, if I'm just going to push deploy here, I did some code change to deploy, it's going to compile everything. It's going to build a new image, a new Docker image representing that, and it's going to do automatically a rolling upgrade for my, my function. Okay, so that's an approach that we think makes more sense when you're building those pipelines, because essentially all the stuff around generating feature vectors, doing inferencing, even doing ETLs could be delivered using serverless functions, and trying to even automate the path between the data science using Jupyter and serverless functions. Now, another thing here is that all this data can also be visualized in Grafana, because Grafana accesses the same data, and Grafana is yet another Docker container on the same Kubernetes cluster. So if I want to now go and emulate this entire solution, this is emulating the overall solution, so I can just go and generate sensor data, and I could go and see my machines, and maybe even zoom into the statistics of my machines. All of that stuff is working exactly on the same cluster, and it's all fully integrated. So what you've seen, as I mentioned, first you ingest. You can use functions to essentially break the JSONs or whatever into feature vectors, and also do the joining in order to create the correct feature vector. You can contrast it with the model, and then you could visualize it with all those tools on a nice Kubernetes cluster. Okay, a few more minutes, a couple of minutes. Okay. Sure, so let me close that, sorry. Okay, so just a few words on some use cases. So if you want to make something more real, this is a network cybersecurity. We're working on some of the telcos on the same solution. You can think about all the data from the network, net flow feeds, information from routers and switches, and being able to predict exactly where is going to be a failure, when there is an attack. It's extremely high concurrency. The traditional architects will probably look something like that. The solution that we've came up with is, again, this sort of Kubernetes cluster, Nuclio doing all the netflow classification, sensor data classification, Spark doing prediction in real time on the same data. Presto is being used as a way to translate all the same data to SQL language for their tools, like in this case, doing real-time network rerouting, changing the router behavior based on SLA of the network and predicted SLA of the network. And all the same data is also accessible to things like Tableau and other based on the same architecture. So give me one more minute. Okay, so I'll skip I had another interesting video, but anyways, just to summarize, we believe this is the right approach to build sort of continuous and real-time analytics flows, which is, again, trying to move from traditional Hadoop frameworks to something which is more microservice-y, serverless, Kubernetes, et cetera, and combine all those technologies. So with that, I'll have to close. Any questions or comments?
Yeah, I'm really sorry, but we are out of time. We started a little late. It was extremely interesting. I'm sure we all wish we had time to continue. Thank you a bunch, Yaron.
Welcome.